Okay, so the last thing we discussed last time was the ergodic theorem. I want to make a few remarks before I proceed. Okay, I mentioned actually a special case of it in the sense we said that if t is so I have my dynamical system. So this is measure preserving. And when I stated the ergodic theorem, I also mentioned that T is ergodic, but actually this is not important. You still get conversions, but then the answer is not as nice. When T is ergodic, then we said that for any f integrable, if I look at the average of f along an orbit, so this is just measuring along one orbit, that this converges to the spatial average, so the integral of f, and this happens for mu almost every point x. Why we like this theorem, for example. Let's just take a very simple example. If f is the indicator function of a set, so suppose you want to measure the frequency of certain digits, and as in the examples that we have mentioned, like let's say I'm interested in a block 0, 0, 1 or whatever, so A will be the interval where this block takes place. Then if you plug it in here, the left side is just measuring the number of times your orbit is in the set A, so how often is Tix in A, and this is saying on the that this is equal to the integral of the indicator function, which is the measure of the set. So the ergodic theorem tells you the frequency of occurrence of anything, any block of digits, or actually any other thing if you want to measure it. Okay, so let me just make a small remark that if T is not ergodic, if I just have a measure preserving system, that is, if you only have measure preserving, which means you only have stationarity, then you still do get conversions, but then the answer is not the integral, it's not a constant, this is a constant. Then the conversions would depend on x. That this converges to some function, let me call it f star, that depends on x. But f star has many nice properties. F star is integrable, has the same integral as the original function, and it's T invariant. Of course, it need not happen everywhere, but mu almost everywhere, which is good enough for us. And in the characterizations of ergodicity that we mentioned on Monday, if you have ergodicity, sorry, this is f star. If you have ergodicity, then any T invariant function is a constant, and then the constant would have to be the integral. Okay, so yeah, and also when I motivated the ergodic theorem, I said it's like a generalization of the strong law of large numbers. And in the strong law of large numbers, you had independence, and you had identical distribution, which is stationarity. And I said independence is replaced by ergodicity, which is some kind of a weak independence. So let me elaborate on this a little bit. And this is actually a corollary of the ergodic theorem, which says that T is ergodic if and only if for any two sets A and B measurable, if I look at, it's not really independence, but asymptotic average independence, if you like, that the limit as n goes to infinity of 1 over n, the sum from 0 to n minus 1, and this is the measure of T minus I A intersection B, that this is equal to the product of the measures. Of course, independence really means usually that independence usually means that mu A intersection B is just the product measure. And here you don't have this, but it says that if you fix one and move the set, the other set around and take the average of the measures, then you do get the product of the two. So that's why it's some kind of an independence idea. The proof is actually very simple, and it's just a consequence. Maybe I'll just do a few steps. So let's look at the proof of this. And let's assume T is ergodic, so let's go this way. And if you look at the equation we want to prove, it's really the integral, and this is of the characteristic function here. And one characteristic function is fixed, doesn't depend on n or on I, and the other one is moved around. So in fact, if you look at this, it's just the integral of the indicator function of this intersection, which is just a product, indicator B, and then indicator of this set at x, which I can also write it as A at Tix. So this is the integral of these guys. And if I move the sum inside, then you see that I'm talking about ergodic averages of this indicator function. So by ergodicity, we have that limit as n goes to infinity. If I just look at this, let's forget indicator B for a second. This, by the ergodic theorem, converges to the integral of indicator, which is just a measure. So now, and this happens mu almost everywhere. So now if I multiply both sides by indicator of B, because that's what I want the product. So if I do indicator of B, which is of course independent of this limit because I'm not moving things around, then I get indicator B here, and it's still happening mu almost everywhere. And now I'm in a lucky situation. I want to integrate, and I want to move the limit inside, so I have to use dominated convergence theorem, but I have no problem because this sequence is bounded by 1, and I am in a probability space. 1 is integrable, so I can apply Lebesgue dominated convergence theorem. I integrate both sides and move the limit inside. Then I end up with the integral of this guy. Of this guy, which is just what I have here. So just let me write the answer. So the integral of the left side is exactly the expression on the left here. And this converges to the integral of the right side. Mu A is a constant. And if you integrate this, you get mu of, this is A, and you get mu of B. So that's one side. And the other side is also almost trivial. Let's see. So let's go this way. Suppose I have this condition for any A and B, and I want to show T is ergodic. And I had these 5 characterizations. So I have a choice in which characterization I want to use to show T is ergodic. So I'm going to use just the definition that any T invariant set has measure 0 or 1. So let's pick a T invariant set. So if now I apply this star. I have star is true. I apply star with A and B equals to E. Then I get on the left side, so from star, I get this mu of T minus IE intersection E, that this should go to the product of the two measures, which is mu of E squared. But on the left side, if you look at the left side again, because of invariance, this is actually just E, This is just E. And E intersection E is E, so this is just mu of E, adding it n times, dividing by n, so the left side is actually just mu of E. So you end up with mu of E equals mu of E squared, and that, because I have a probability measure, that says mu of E is 0 or 1. So, so T is ergodic. So this is nice because, as I said, it just says that ergodicity is just some kind of a weak independence. And not only that, it also motivates other definitions of independence or weak independence that are stronger than this. Let me just write definitions, but I don't want to elaborate on them. The idea of mixing. So using this star definition, you can sort of weaken or strengthen actually a little bit this. So for example, these are just definitions in case you see them later. So we call T is weakly mixing. If, of course, star, you can rewrite it in a trivial way by bringing the left side in. So you can, is mixing if you have this. But now the absolute value of the measure of T minus IA intersection B minus the product is 0. And of course, absolute independent convergence is stronger. So weakly mixing implies ergodic. And you can go one step further, which is even better. Here we're taking averages. You can actually remove the averages and just see when is this going to 0, and that's what we call mixing. So this is definition 1 is the weakly mixing, and 2, T is mixing or strongly mixing. Some people, if you want to distinguish the two. Of course, here is for every A and B measurable, and here too. You have limit. And this is as close as you can get to independence, namely mu of T minus NA intersection B is the product. And because these sequences are positive, etc., so you can, it's clear that strongly mixing implies, weakly mixing implies ergodic. For example, the continued fraction map is in fact strongly mixing. And in the proof of Valerie yesterday, she was proving ergodicity, but in fact the proof shows it's strongly mixing. Okay, so let's see what other things I want to say. Yeah, and also she mentioned about two ergodic measures being equal or mutually singular, so maybe I will elaborate on that as well. The proof is kind of very easy using the ergodic theorem. Okay, let me do this. Okay, so you have this little theorem. So we have first. Let's not talk about measures for a second. So I have this probability measure space. And we can put lots of measures there, and we can put lots of invariant measures. Sometimes there is only one. That's the case where people say it's uniquely ergodic, but usually there are many invariant measures. Okay, suppose mu1 and mu2 are two invariant measures. So mu1 of T inverse A is A, and the same thing for mu2 of T inverse A is mu2 of A, sorry. Okay, I'm going to mention two things, but well, maybe I'll prove both. So the first thing is that in a measure class, in a class of absolutely continuous measures, the ergodic measure is the smallest one. So if mu1 is ergodic and mu2 is absolutely continuous with respect to mu1, so all mu1 sets of measures 0 are also mu2 sets of measures 0, then mu1 is mu2. So the ergodic measure is the smallest one, in a sense, in this class. And the second one is that if mu1 and mu2 are ergodic, then either mu1 is mu2, or they are completely mutually singular, which means their support is disjoint. They have disjoint support. So mu1 sees another part of the space than mu2. Okay. Okay, the proofs of both are easy. So maybe I'll just sketch them. So proof of 1. Okay, so I want to show that these two measures are the same. So I want to show that for any set A, mu1A equals mu2A. Okay, so I pick any set A in F. And I exploit the ergodicity of mu1. So I apply the ergodic theorem to mu1. You have that, let me write it as a set. Okay, let me write down the set CA, which is equal to, the set C. Why did I write CA? Oh, sorry. So because A is fixed here. CA is the set of all X in your space for which the ergodic average goes under mu1, goes to the measure. That's by ergodicity. Because this conversion happens mu1 almost everywhere, this set has mu1 measure equals to 1. So let's say mu1 of CA equals to 1. But because these two measures, because mu2 is absolutely continuous with respect to mu1, any set of mu1 measure 1 has also mu2 measure 1. So by absolute singularity, continuity, mu2 of CA is equal to 1. So this means with respect to mu2, almost every point, you have also this convergence. So let me take this, and this is a bounded sequence. So I'm going to apply again the Lebesgue-dominated convergence theorem, but with respect to the mu2 measure. So by Lebesgue-dominated convergence theorem, with respect to mu2, if I integrate this, bringing the limit in blah, so you end up with a limit as n goes to infinity, 1 over n, sum I from 0 to n minus 1, the measure of this, and by measure preserving, of course here, if you put this down, this is like t minus IA at x. So I get the measure of t minus IA, but because of measure preserving, it's the same as the measure of A. So the left under mu2. So the left side after integration and using measure preserving is simply this. And this is equal to the integral of the right side with respect to mu2. But of course, this is simply a constant. So the left side is just mu2 of A. And the right side is just mu1 of A, because mu2 is a probability measure, and this is a constant. So in this way, we have shown that for any A in F, mu1 of A equals mu2 of A. So the two measures are exactly equal. So you can see the ergodic theory is very strong. It gives you many consequences, many results. Let me do 2. Maybe I can do this up. It's hot. OK, so let's do 2, which is what is that? Yeah. So if you have 2 ergodic measures, then they are either equal or mutually singular. So let's assume they're not equal, and I'm going to show they're mutually singular. So suppose mu1 is not equal to mu2. This means that I can find a set A measurable such that mu1A is not equal to mu2A. OK, great. And now I am, my assumption is that both measures are ergodic. So I'm going to apply the ergodic theorem to the characteristic function of A, first under mu1 and under mu2. So let me write, let's see, I of 1 or 2. To be the set of points for which the limit of the ergodic averages of the indicator function of A equals mu I of A. So by ergodicity of mu1 and mu2, I know that mu1 of C1 is 1, and mu2 of C2 is 1. And not only that, C1 and C2 are disjoint, because you cannot have two distinct limits, right? So, and C1 intersection C2 is empty. So here we go. So mu1 lives on C1, and mu2 lives on C2, and these are disjoint. So you have mutual singularity. OK, so in any measure class, you can have only one ergodic measure. OK, let's see. What did I want to say? Yeah. So before I go back to the examples, I want to do one more lemma, which is Knopf's lemma. It was also mentioned yesterday. And this lemma is actually very old, but not very well known. But it's a very useful lemma to show ergodicity, especially if you have maps that are monotone. So let me do that. So that I don't make mistakes. Yeah, in the notes it's mentioned for Lebesgue measure, but actually it's true for any Borel probability measure on the interval or the real line. But yeah, it doesn't matter. So let be. In here I'm saying Lebesgue set. It can also be Borel, but because we're doing measure theory, so it doesn't matter if you take a Borel set or a Lebesgue set, because they differ by a set of measure 0. So let B be a Lebesgue set, and yeah, okay, so no assumption. And B and C, a collection of intervals satisfying the following condition. Following two conditions. And again, 0, 1 is not important. Any interval, any interval of the reals. So, but we can always normalize and work on 0, 1. Okay, the first condition is that this collection C generates, or that any open interval can be written as a countable, or finite, of course, so as a countable disjoint union of elements of C. And the second condition is that this set B intersects every element of C with a fixed proportion. I'm not saying it correctly, but what I'm saying is this, that lambda, as I said, I'm writing it lambda, but it can be any Borel measure here. Lambda of A intersection B is greater or equal to gamma times lambda of A, yeah, for every A in C, and gamma is positive and independent of the A's. So a universal constant. So if I can find a universal constant with this property, then the conclusion is that the measure of B is 1. So B has to be big, almost all the space up to sets of measure 0. So of course, in the applications, we will start with a T invariant set B, and we're going to find a good collection C, and then we're going to show that the measure of B is 1, and this will prove the ergodicity. So it's a very useful lemma. Okay, and the proof is few lines, really. So let's do it. Okay, so let's assume that measure of B complement is positive, so actually by contradiction. And I'm going to, we know that open intervals generate the Borel sigma algebra. So I'm going to approximate B complement with the finite union of intervals. So let's say, so let epsilon be positive. So let's write there exists an E epsilon, which is a finite disjoint union of intervals. Such that the measure of B complement, symmetric difference E, that this is small. So I approximate B complement with a finite disjoint union of intervals. And then, so E is a finite disjoint union of intervals. I don't know, I write something like this. And for each interval, I apply 1 and 2. So I write each interval AI, BI as a countable disjoint union of elements of C. And and for each one, I apply this thing here. So let me just be brief here. So by 1 and 2, it's very easy to see that. We have that if I do lambda of B intersection the E, so each E is written like this, and each one is written as a countable union of elements of C. And for each one in this countable union, I have it's greater than gamma times the lambda of this measure. So you end up with this greater than gamma times the measure of E. Yeah, so it's an easy thing. Okay, so now let's come to the contradiction. So now I go again to, so I have this here. So again, I look at this set, this measure. Okay, of course, symmetric difference is B complement minus this union this minus the complement of this. So I take just one part of this 2 union, namely I take this minus B complement. So this is greater or equal to the measure of B intersection E. That's the second part of this union. Yeah, and then let me see. And then I apply what I just got here. And then in a trivial way, this is bigger than if I intersect it with B complement. Like this. And then, yeah, OK, let me write it, and then I'll just briefly say it. So this is gamma bigger than gamma lambda of B complement minus epsilon. OK, let me just say a word here. It's actually very easy. I simply write lambda B complement as lambda B complement minus E plus lambda of B complement intersection this. And this is less than the symmetric difference. And this is less than epsilon. And just I moved the epsilon there. So that comes from here. OK, and also from our assumption of this is less than epsilon. So you have epsilon is greater than this, and it's less than this. So you will end up with, I have epsilon is greater than gamma times this guy. So if you solve, you only take the beginning and the end. You end up with lambda of B complement is less than epsilon plus over gamma plus epsilon, something like this. And epsilon is arbitrary. So this says lambda of B complement is 0. OK. OK, so let's now we can go back to the examples now. Can I erase this part? This part? Okay. OK, so let's go back to the examples. Let's first start with the integer base. OK. So back to the examples. So let's start with the first example, which is the 2x modulo 1. But any mx modulo 1 is also the same proof, really. I didn't talk about isomorphism, but if I were to do isomorphism, then you see it's a shift. And to prove that the shift is ergodic is also easy. But anyway, also Knops does it very easily. So here, Tx is just 2x modulo 1. But as I said, everything I do here is also true for any, instead of to any integer. So this is my map. OK, so I want to show this map is ergodic, and I want to apply Knops lemma, which I just erased. That was not the point, but good. OK, so for Knops lemma, I need the, OK, I'm going to take a T invariant set, and I'm going to show has measure 0 or 1. OK, and I'm going to assume it has positive measure, and then I will show it has measure 1. So let me start like this. So let T inverse E be E. And assume mu of E is positive, and my aim is to show that it has measure 1. OK, so now I have to get this collection C. And the collection C is just the dyadic intervals. So let's see. Be the collection of dyadic intervals, that is k over 2 to the n, k plus 1 over 2 to the n. Here n is, I guess, 1, etc. And k is 0, 1, up to 2n minus 1. Like this. OK, now this collection generates. Anything can be approximated by dyadic rationals. You can also see it because the dyadic rationals are dense. And you can also see it because these are intervals and the diameter shrinks to 0. Anytime you have intervals with diameter shrinking to 0, they are generators. OK, so this generates. So this satisfies 1 of Knopf's lemma. And now I want to do 2. So I want to show that E intersects every dyadic rational by the intersection is greater than some constant times the measure of the dyadic rational. And the trick is very easy, actually. What you do is I take this set E. OK, before I want to mention a few remarks. OK, this is T. And the basic partition is 0, half, half, 1. The first, when n is 1 and k is 0 or 1. And if you start, if you look at these guys, that is, if you start looking at higher iterates of t, like, for example, if I look at t squared, that is t composed with t, then you end up with the map 4x modulo 1. So t squared is, in fact, just simply this thing here. So just 4x, 4x minus 1, 4x minus 2, 4x minus 3. So the dyadic intervals with n is 2 of order 2 are the basic partition for t squared. And you can see that on each interval, t squared in this case is full. That is, take this interval to the whole thing. And in general, if I look at Tn, then you get 2 to the n branches. And the dyadic intervals of order n are the basic partition. So I know that there are lots of them. So let me just take one of them. So here's k over 2 to the n. And here's k plus 1 over 2 to the n. And on this interval, the map is what we say full. So the map here is 2 to the n x minus k. OK. So for 2, I have to pick any element of C. So let me pick a dyadic rational. So any arbitrary element of C. Let's say it's order n, so it looks like this. So I know that if I look at Tna, then I get the whole interval like this. OK, so let me go back to this picture, and I'm going to magnify it just so that you see the picture. So this is a magnified view. This is my interval. This is my A. And this is what Tn is. And now I take E. And so I'm interested in lambda of E intersection A. And I want to show this is greater or equal to some gamma independent of A times the measure of A. Yeah? So I first exploit the invariance of E. E is invariant here. So this is lambda of, because I have order n, so it's convenient to look at T minus NE. Of course, it's still E. But now what I do, here's my E, somewhere here. It's not an interval, but let's just make it look like an interval, just to see it clearly. Here's my E. And when I look at T minus NE, of course, I'm going to look at all the inverse images. I'm going to get inverse image in every dyadic interval, but I'm only interested in that part that is here. So this part here is T minus NE intersection A. Now, luckily, this map is linear and it's full. So when I go back, I'm shrinking E by the slope, by the measure of this slope. So this guy here has measure, in fact, the map has slope 2 to the n, so I'm shrinking it by the slope because I'm going backwards. And so it's just 1 over 2n, the measure of E, simply. And this is very important that I have full lines. That's allowing me to do that. And I'm done, because this is the measure of A. A is dyadic interval, so this is just lambda of A times lambda of E. And this is my gamma. I assumed E has positive measure, so this is my gamma. So for any A in this collection C, which is dyadic intervals, this measure is equal to, actually equality, not even greater, because it's mixing, in fact. Okay, so that shows ergodicity. Okay, let me, before I go beta expansions, let me go to the Luroth series because it's the same idea. I have till 12, right? 12 o'clock? I have half an hour, right? I don't know when I started, but not so much. I think half an hour is more than enough. Yeah, I'm fine. Maybe even earlier. Let's see. Okay, so let's go to the Luroth series. You see, Luroth series are really the same as these guys. The map looked like this. The basic partition is like the continued fraction, so I have the half, a third, etc. And on each interval, I have complete lines. And that's really what's important. It's exactly the common denominator with the 2x modulo 1. So I have all these complete lines. Let me write down the map. Okay, so the map looks like Tx equals n minus 1 x minus n minus 1 on the interval 1 over n minus 1. Here, n, I want n to start greater equal to 2. So here the digit is 2, here 3, here 4, etc. Yeah? Oh, I missed something. I didn't say that. In this case, Lebesgue measure is invariant. It's very clear, because if you take any set, that's why I was working with lambda. Because if you take any set, it's enough to take intervals, AB, and if you, so the measure of AB is just B minus A, and if you look at inverse images, then you get 2 of them. This guy here, and this guy here. This is A over 2, B over 2. And this is A plus 1 over 2, B plus 1 over 2. And of course, the measure of AB, which is B minus A, equals the sum of these two measures, because this is B minus A over 2, and the same thing here. And that's what I want to say. Every time you have complete lines, Lebesgue is invariant. And the same thing here. So here, Lebesgue is invariant. Let's just do a simple calculation. So I take an interval, which is to show measure preserving, it's enough to take generators, which is intervals. In fact, they can be open, but they just be rigorous and take left close, right open. So here the measure is b minus a, and now I have to look at inverse images, and now I get countably many pieces. So in each, these are what we call fundamental intervals of length 1. So in each one I get a piece, etc. So if you write down exactly what T inverse AB is, you just do the calculation, you know the formula, and you end up with the union n is 2 to infinity of 1 over n plus a over n minus 1, and here 1 over n plus b n minus 1. And these are disjoint. I know the French write it as a product. I usually put the dot here. This is disjoint union. So the measure of T inverse A, B, is just the sum of these guys. And here, if I subtract, the 1 over n drops out, and I get b minus a over n minus 1. And we all know that this series goes to 1, so you get b minus a, which is the measure of A. And as I said, every time you can generalize Luroth series in many ways. For example, I don't need to take positive slopes. I can take also negative. I can do this line like this. I can make a choice which ones I want to write positive slope, which one's negative slope, and they will all be Lebesgue invariant. Okay, so the Lebesgue measure is the right one, the invariant measure, and to show Knopf's lemma, it's really the same idea. And now what I do for C, I also look at fundamental intervals. So let's just define them by just fixing the first digits. So I look at fundamental intervals delta I1 up to, maybe I'll put a bracket here. So here I'm looking at all points whose Luroth series expansion starts with this, these digits, which means I'm looking at all points x in the interval. When I expand them, I start with 1 over I1, and then 1 over I1. I have to remember I1 minus 1, I2, and then the last one will be I1 minus 1. I don't know where I stop. I think at I, something like, wait, let me think. Ik minus 1, Ik minus 1 minus 1, and then Ik. That's the first k terms, n terms. And this is the leftover. And the denominator here is the same thing with in minus 1 at the end. So the denominator is I1 minus 1, blah, 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 until in minus 1. And these are T and Tn are, you know, they all go from 0 to 1. So you can see that the smallest I get in this set if Tn is 0, so I get this as my left endpoint, this sum. And the largest, if this is 1, then I get my right endpoint, this plus this. So this is really the interval. Lots of writing, but 1 over I1 plus blah, 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 what I had here. In. Maybe I should save myself the trouble. Let me call this Pn over Qn. Plus 1 over this. Yeah, like this. So this is really this interval. What do I want to say? Yeah. And on this fundamental interval, the map I should look at is Tn. And let me just say that Tn of delta I1, same idea as in the binary, is actually the whole interval. So these are what we call full fundamental intervals, because you get mapped to 0, 1. Okay, so it's really the same setup. So, and moreover, the slope of Tn on this fundamental interval is in fact, let me think, is in fact what you see here. Let me see if I'm right. Don't have it here. This guy up to here. So the slope is 1 over, sorry, up. So the slope is I1 minus 1 up to, up to In minus 1 I get with a minus also, and then In. So this is the slope of Tn on this delta. And this is also, if I'm not mistaken, I think I made a mistake somewhere. Maybe it's this up to here. I don't know anymore. Let me see. I guess I'm saying that the slope, yeah, slope is here, and this is the, but it doesn't look right. And I'm saying this is the length of delta I, but it looks to me like the length is up to here. Maybe this is up to In. I don't know anymore. But this is also, it looks a little bit, something is wrong here. But this is also, I have to write it down, and that the measure of this guy is 1 over, it should be 1 over this guy, actually, but it doesn't look right what I'm writing.
It's right over 1, so just the difference.
Yeah, I know, but I want the slope to be 1 over the measure of this interval.
Exactly right. So
is it?
It's equal of that, and then you made a mistake here.
Where? Here?
Yeah, this is correct.
Here I made a mistake. Where they are? Ah, here.
Yeah,
Up to here.
and change to n, minus 1 to n.
Like this. Thank you very much. Etc. So the length is 1 over the slope. Yeah. And as you can see, it's the same calculation. What I did there also, the length of my intervals was 1 over the slope. So it's the same thing. That is, if I take an invariant set now, so my C, so now my collection C is just the collection of these fundamental intervals. And for all possibilities of the i's, ij is greater or equal to 2. So these are my C. And these generate, again, an easy way to see that is that because the length shrinks to 0 and they are intervals, so they generate. So this satisfies 1. And to get 2, it's exactly the same. So I pick an invariant set, E. Let's call it E. And let's assume it has positive measure. And I do the same trick. So for any set A in C. Let me just call it delta, because now this is what I'm calling them. For any delta in C, if I look at lambda of E intersection delta, then I exploit invariance, and I replace this by t to the minus n. And the same idea, if you take E and you look at t minus ne, then it will intersect every fundamental interval. But I'm only interested in that intersection in this delta. And so I will get that I'm shrinking this measure by the slope of t to the n on this, which is what I wrote there. So it's just the slope, which is 1 over delta, the measure of delta. Sorry, the delta itself. 1 over the slope is the delta. Yeah? Of the measure of E. And in this case, again, this is gamma, and I get exactly equality. So in fact, binary expansions, M expansions, and all that are sort of belong to the same family, which we call generalized Luroth series. So every time you have an map of the interval where you have partitions, interval partitions, and where the maps are complete lines, then the behavior is all the same, exactly identical. Okay, so let me, in the last 15 minutes, just look at beta expansions, because these are not full. You have lines that are full and parts that are not full. So you have to remedy this a little bit, but it's really not a big deal at all. Maybe I'll move this down. Okay. So let me look at beta expansions, and in particular the greedy, which is usually in the literature called beta expansions. So my third example is beta expansions. So these are the greedy, because as I mentioned the first time, there are many ways of doing beta expansions, but we're going to do the greedy case. So I have something that looks like this, depending on the integer part of beta. I have, and not only that, okay, I'll mention it again. When I mentioned it the first time, I sort of worked on a bigger domain. And I keep going until greatest integer beta. Let me make them smaller. So assume I went up to anti-beta here, like this, and then this was the figure. So this was beta x minus 1, beta x, let's say minus the greatest integer, let's say I blah, blah, blah. No, minus 1. And this is beta x minus greatest integer. Okay, and one lies somewhere here. I'll do blue. One lies somewhere here, maybe. And this part, as I mentioned last time, is an attractor. So once you're in 0, 1, you never leave it. And if you are here, every time you apply t, you start moving bit by bit to the left. Eventually, you enter 0, 1, and that's it. And the support of the invariant measure must be invariant. So in other words, I cannot have any mass here under the invariant measure. So all my measure should be supported on this guy. So on this part here. And on this part, on the blue part, the map is simply beta x modulo 1. And also, because I don't have now complete line here, it's really very easy to see that Lebesgue measure is not invariant. Yeah? So Lebesgue measure, which I usually know by lambda, is not T invariant. And as I mentioned in the 60s, actually Golfin got it before Perry. Let me see the dates. I think Golfin got it 59 and Perry 60. Yeah, and I don't think Perry was aware of Golfin. But anyway, they found the invariant measure. And it looks like it's absolutely continuous with respect to Lebesgue. And in fact, it is equivalent to Lebesgue on 0, 1. So invariant measure equivalent to Lebesgue. Has density. Okay, let me just write the density. Has density. Let's call it H. Of course, it depends on beta. And it's some normalizing constant that depends also on beta, just to make it probability measure. And this here is sum. It depends on the orbit of 1. Is really determines everything. Even determines whether, if I give you a sequence of 0, 1 up to greatest integer beta, to check if this coming from a beta expansion is also determined by the expansion of 1. But I haven't mentioned it, so 1 is crucial. 1 determines everything, in fact, the orbit of 1. And this is simply indicator 0 Ti of 1. X over beta to the I. Yeah, correct. And I goes from 0 to infinity. This is the invariant measure. It's piecewise step function. And in fact, if the orbit of 1, if the expansion of 1 is finite, you only have finitely many pieces. But if it's not, then you have infinitely many pieces. And this is the density of the invariant measure. So mu of A is simply the integral of H beta of X over A d lambda. Okay, but because, let me write down again, stress it that mu is equivalent to lambda on 0, 1. So in other words, if I take a T invariant set, so if I have a T invariant set and I want to show it has mu measure 0 or 1, it's enough to show that it has Lebesgue measure 0 or 1. So I can reduce all the calculations to Lebesgue measure. Okay. Now, as you can see, I can also work with fundamental intervals, and that I will do. But the problem is I have these if I only work on 0, 1, these guys are full, and this is not full. But it's no big deal, because let me make a simple example like the golden mean. Yeah, in general case, you have to do a little bit more work, but it's really the same idea. So I'm just working with 0, 1. And the golden mean looks like this. OK, this is not full, and this is as Pierre mentioned yesterday, it's beta minus 1 or 1 over beta in this case, because it's the golden mean. OK, this is not full, but the next time everything gets mapped here. So at level 1, this is not full, but if I do level 2, it will be full. So what I'm saying is that if I wait enough, any non-full interval can be covered by full intervals. In other words, full intervals generate the sigma algebra. You start dividing, so this was not good, and then the next time it will be full. So this is delta 1 is not full, but if I look at it as delta 1, 0, it is full. Yeah? So So all I'm going to say now, just and it's in the notes written rigorously. So C is the collection of full intervals. That is the intervals whose image is the whole real line, 0, 1, sorry. And these generate the sigma algebra, the Borel sigma algebra, or Lebesgue, whatever you like. So they satisfy condition 1 of Knopf's. So that's the whole thing. Okay, I have problems, but no problem because the full one will save me. They will cover the non-full ones. And then the rest is the same as in the Luroth and what was it, the binary. So I do the same thing. I take a T invariant set, and I assume, and as I just said, because of equivalence, I can work with Lebesgue measure. And now I take an element of C which is full. And they are also, so I look at fundamental intervals. So these are all points whose beta expansion starts with I1 up to IN, B and C. So because it's full, then let me just make like remarks. Then lambda, Tn of delta is the whole real line, is the whole interval. And slope of Tn on delta is beta to the n. That is the length of n fundamental intervals, of n full fundamental intervals is actually 1 over beta to the n. And then the rest is the same. So you take a set E, you move it down, and you end up with the same conclusion, that lambda of E intersection this delta. I replace E by T minus N, etc. So this is just the same thing again. Yeah, okay, I'm repeating myself. So I do minus 10 T and E, intersection delta, and the same conclusion as before. This will have a proportion of 1 over beta to the n of the measure of E, lambda of E, and this is the Lebesgue measure of this interval, and I'm done. So gamma is again lambda of E. Yeah. Okay, so and you get that E has measure 1. Lambda of E is 1, and that means mu of E is also 1. Okay, so next time, although Pierre will talk about natural extensions, but I was also planning to do that. So I'll see, depending on what Pierre does, I might change my talk a little bit. So I think that's it for today. Yeah.